So scientific notation. We're going to talk about what it is, why it's important, and then we're going to do some example problems so that you'll get really good at this stuff. So scientific notation is like an abbreviation. It's a shorthand way to write numbers that are really big and really small. Here's why that's important. In science, we spend a lot of time dealing with really huge numbers. For example, this is the number of miles that it is from Earth to the closest star outside of our solar system. A really big number. We also look at a lot of really small numbers. This tiny number is the amount of time that it takes for light to go from one side of an average sized bedroom to the other side. That's about 30 feet. Okay? And these numbers aren't even the biggest and smallest that we use a lot. This is the number of atoms in an average sized glass of water. And this number is the weight in pounds. Notice there's a decimal place here, so it's a really tiny number. This is the weight in pounds of a proton in an atom. Look at all these zeros. These zeros are such a pain, right? Imagine having to multiply this number by this number, or do division, do any of this by hand. It would be such a pain. Even if you're using a calculator or a computer, just typing in all these zeros and making sure that you haven't forgotten one or added in a couple more, that's really a big pain. So scientific notation comes in handy because it lets us take numbers like these really big ones and these really small ones, get rid of all of the zeros, and write them in a very compact, very simple way that's much easier to use. Let me show you how we do it. Let's start with this really big number in miles. Here's what we do to compress it down and write it in scientific notation. The first thing is we figure out where would the decimal place be. A lot of these numbers won't actually have a decimal place written, but you know that it should be right here. So I'll write in where the decimal place would be. There it is. Now I move it and I count the number of spots. Watch what I do. I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And here is the new spot. I move it until the decimal place is sitting here and there is only one number, one digit I should say, one digit to the left of the decimal place. So the decimal place is here and then one digit there. So I moved it 13 spots in this direction to move it to a place where there was only one digit to the left of it. So after I do that, I write the number with the decimal place in the new position. So it's going to be 2.53, and then I get rid of all of the zeros after this 3 here. So this is the first part of the number. Now I need to account for the fact that I moved the decimal place 13 spots in this direction. So I say that I moved it 13 spots in this direction by writing 10 raised to the 13 power. You see this number here, the exponent on 10, is the same number of spots that I moved the decimal place to its new position. So 2.53 times 10 to the 13. I move the decimal place in this direction and I get a number 13 on 10. Okay, now here's a very small number. I do the same, but instead of getting bigger, the exponent on 10 is going to get smaller. Let me show you what I mean. Decimal place is here. It's already written in the number. Watch what I do. I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8 spots. Okay? So now the decimal place is here, and there's one digit that's not a 0 to the left of it. Okay? So 1, 2, 3, 4, 5, 6, 7, 8. I had to move it 8 in this direction. Now I rewrite my number with a decimal place in its new position. Okay, so it's going to be 2.03. And now to show that I've moved the decimal place 8 spots in this position, in this direction, I'm going to do 10 to the -8. So when I move the decimal place in this direction, I get a positive number. The exponent on 10, it goes up. On the other hand, when I move the decimal place in this direction, the exponent on 10 goes down. So I have positive 13 in this direction, and I have -8 in this direction. So I've summed up these rules here. Here's a decimal place. You move it left, the exponent goes up. You move it right, the exponent goes down. It's negative in this direction, positive in this direction. This is the kind of thing that is best learned by just getting a lot of practice. So in this video, we're going to talk about the basics of moles. We're going to learn about what they are, and we're going to talk about some of these important numbers and terms. Now, we're going to start from the very beginning on moles here, so no matter how much you know or how much you don't know about moles, this video will be a great place to start. So what's a mole? I'm not talking about the cute little furry creatures that live underground here. I'm talking about the kind of moles that are super important in chemistry. So a mole is a name for a specific number of things, okay? A mole is kind of like a dozen, right? A dozen is the name for 12 things. There are 12 things in a dozen. Now a mole is like this, but it's way bigger than a dozen. 12 things in a dozen. In a mole, there are 602 hexillion things. This is 602 followed by 21 zeros. 602 hexillion things. So a mole, like a dozen, is a name for a certain number of things. There are 12 things in a dozen. There are 602 hexillion things in a mole. This is a gigantic number. Now here's one thing that confuses people about moles. They forget that a mole is a name for 602 hexillion things, and they think that a mole is an abbreviation for the word molecule. So many people think this. They see mole and they think, oh, you mean molecule. No, no, no. If I write mole, I don't mean molecule. I mean a group of 602 hexillion things, not a molecule. So there are 602 hexillion things in a mole. And just like a dozen, we can have a mole of anything, right? So we could have a dozen donuts, which would be 12 donuts. Or we could have a mole of donuts, which would be 602 hexillion donuts. Or hey, we could have jelly beans. A dozen jelly beans would be 12 jelly beans, and a mole of jelly beans would be 602 hexillion jelly beans. So sometimes people get freaked out about moles, but just remember they're a lot like a dozen. 12 things in a dozen, 602 hexillion things in a mole. You can have a mole of donuts, you can have a mole of jelly beans, a mole of cars, a mole of paper clips, a mole of bouncy balls. Just as long as it is 602 hexillion things, you got a mole. Now let's talk a little bit about this actual number, 602 hexillion. This number is often referred to as Avogadro's number in honor of the Italian scientist who discovered it. But now, check this out here, right? 602 hexillion, this is a gigantic number. 602 with 21 zeros after it. Think about what a pain it is to deal with this number, right? If you're doing math by hand, you gotta write this out and like do your multiplication and division with 21 zeros. Even if you're using a calculator, you gotta type in all these zeros and make sure you have the right amount. And then when you get your answer, you gotta go back and count how many zeros your answer has. It's a total pain. So instead of writing out 602 hexillion with all these zeros every time we want to talk about moles, we tend to abbreviate this number. Now, as you may know, when we abbreviate numbers in math and science, we usually use a technique called scientific notation. And here's how we would abbreviate this number using scientific notation, okay? I got this big number, 602 hexillion. I find out where the decimal place would be. It would be right here. And now I move the decimal place until I have just one digit to the left of it, okay? And I count the number of spots. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. And now this is my new spot because there is a 6, just one digit to the left of it. So I moved my decimal place 23 spots to the left. And that means that in scientific notation, I would rewrite this number as 6.02 times 10 to the 23rd. The 23 comes from the number of spots that I moved it to the left.